Hello. So today I'm going to be just assessing a variety of SNARK schemes in the literature which I find interesting. I've by no means covered everything, but if you happen to think of something that you think I should have included, which I haven't included, then send me an email because it's possible I haven't heard of it. But my aim of this talk really is to say, these are the pairing-based SNARKs we know of. When would you use which different scheme? So fairly high level. So what is a SNARK? I would say the simplest explanation is that it is a tool which you can use to build applications which require privacy and integrity at the same time. Okay? So privacy without integrity is very easy. You can just send something which isn't true. Integrity without privacy is also very easy. You can just send something. But having them both at the same time is something which cryptographers have spent decades trying to find better ways to do. So what do we require? We require that it's correct. An honest prover can always convince an honest verifier. We require that it's zero knowledge. So a malicious verifier learns nothing from an honest prover except that their statement is true. And we require that it is knowledge sound. Namely, only a prover in possession of a witness can convince an honest verifier. You can have schemes which are just sound rather than knowledge sound, but this extra knowledge property gives us more power when we're trying to build applications. When would you use them? Anonymity is a big one when you're trying to where you might not necessarily care if people know what's inside the thing that you're hiding, but you want to keep your identity secret. You might use them when you want something to be private, so you don't mind if people know who you are, but you don't want them to know what you're doing. And also a big application of SNARKs specifically is scalability. If you want to convince someone that something is true, but you don't want them to have to go through all of the work that you've done in order to compute this thing, then you might use a SNARK. And this is something that you wouldn't get from other zero-knowledge protocols. There are some that you could use, like STARKs, but I don't think you could use bulletproofs for that because you have linear verification time. So before diving into the SNARKs, I'm just going to talk briefly about some situations where you probably wouldn't use a SNARK. The first one being if you want to prove a one-off large computation has been proved correctly. And the key thing here is one-off. SNARKs are only useful if you're proving the same thing over and over and over again, because essentially how they work is you're putting a lot of the verifier's work into this big pre-computation, which they do at the start and then they never have to do again. However, doing that big computation, if you're only going to prove something once, just isn't worth it. So if you have quite a large computation, you'd also probably want something that uses symmetric cryptography. And this has the added bonus that it is feasibly post-quantum secure. And we have a couple of different ways for doing that. The other situation where maybe you wouldn't use SNARKs is if you're proving something very, very small. Because with SNARKs, we're using pairing-based groups. The verifier has to compute pairings. This is an overhead. This is an overhead that you probably wouldn't want to pay if you only have 10 gates. So as far as I'm aware, most of the schemes you'd want to use for this would be discrete log-based. And again, there's some options for that. Oh, another situation, if you're trying to prove something very specific. So SNARKs are for general computations, situations where you don't necessarily have a specific protocol, but you want to prove this thing, and here's a scheme that you can use. But there are some schemes in the literature for which we have better proofs, where you might not want to do the NP reduction, so reducing it to a set of R1 CS constraints, because that's expensive. So the situation where you would want to use SNARKs, and I am thinking pairing-based SNARKs here, although I'm aware that there are others, is when you're trying to prove the same constraints are satisfied multiple times. So really what you're trying to leverage here is that you can get improved efficiency if you use pre-processing, this large computation you do at the start. And I would really say that SNARKs are probably the best option for this at the moment. So why are they good? They have very, very small proof sizes, constant sized. Likewise, they have very, very fast verifier computation, also constant size. A slight caveat there being that the size of the group that you're constructing these proofs in has to be big enough to contain your circuit. But other than that, the downside, we often have to use trusted setup. There are some funky assumptions. They're not broken in any way, but they're certainly less reassuring from a cryptographer's perspective than something like discrete log. And the provers are a bit expensive as well. Saying that the provers are expensive, we do have some that are better than others. And if the only thing you're concerned about in your scheme is speed, the scheme you want to use at the moment is GROT 2016. Okay? This has the smallest proof size and the smallest verifier and the smallest prover in the literature. And the reason is that there was a sort of breakthrough work back in 2013 when people learned how to compile these R1CS constraints into quadratic arithmetic programs and therefore build SNARKs. And after this, there was an explosion of papers which were sort of improving this result. They were saying, if we do this optimization, we can get rid of that group element. And if we do this optimization, we can get rid of that element. And after sort of a few papers, GROT came up with a scheme that was in the generic group model. Okay? So you do lose something from this. It means it's no longer in the standard model under knowledge of exponent assumptions. But it also means that it's a model where you can really cut down on the most elements. So yeah, rank 1 constraint system. The original paper was actually for arithmetic circuits, and rank 1 constraint system came a bit later. But really all it is a clever method for encoding program constraints. So when would you want to use this? Probably in situations where trusted setup really isn't a big deal, and there are situations. Like if you have a closed set of participants that are communicating amongst each other, they can do a MPC at the start, and because it's a closed group, they know that each person knows that they themselves were honest, so they're not worried. Likewise, if you have a method for checking that the original computation was correct, then, so this is what sharks are proposing, then you'd probably want to use the fastest SNARK you possibly can. And also, if you're not worried about decentralization and you actually do have some party that you trust, you could use this scheme. Oh, one other paper I want to mention while we're on the topic of speed is a paper which is talking about how you can distribute the costs of generating your SNARKs. And they don't just talk about the multi-exponentiation, although they do. They also talk about the costs, how you can distribute the fast Fourier transform. And probably the big thing here is they're able to distribute the memory costs as well, because SNARKs are pretty memory intensive. Okay, so suppose now you're not only worried about speed, you're also worried about malleability. And this is the idea that if you have a proof and you also have a destination which you're trying to send it to, but it might be intercepted between you and its destination, is it possible that the person that has intercepted it can change it in some way that would be bad for you? So the example I put on the slides is if you had a malicious peer, they might change the destination address, for example, of where you're trying to send your transaction, and this would be bad. So you probably wouldn't use a simulation extractable scheme if you weren't worried about malleability, because you do pay a little bit in cost for the prover. But if you are worried about it, then the cost is about double, so it's worth doing. So this is actually a scheme that was done by myself in Graz. We built a simulation extractable SNARK. And there are some subsequent works which really get down the size of this prover by introducing the random oracle model. Another situation which I mentioned right at the start for when you'd want to use SNARKs is compression. Okay? So the idea that you want to prove a SNARK of a SNARK of a SNARK that something is valid. And the reason this is quite powerful is where we have constant sized proofs and constant verification time, if you sort of recursively do this, then your final costs are going to be constant. Okay? Your prover might be fairly expensive, but your verifier is going to be very, very cheap. And for some applications, this is very important. So the example I gave before, which is describing this tree type structure that you would use if you were doing this compression, is fairly important, because one thing that we don't want to happen is we don't want to get a non-polynomial time extractor, okay? So with this diagram, we end up with something with logarithmic depth, which means our extractor should still be polynomial time. And and you can sort of make sure of this if you use proof-carrying data, but you wouldn't want to do literally a linear sort of chain of a snark of a snark of a snark. You'd more want to do the tree type structure. One other thing you would need when doing this is you need to prove a proof of a proof, and our proofs require pairings. So we somehow need a way to embed pairing groups inside arithmetic circuits. And sure, you can do this by sort of using binary constraint systems if you wanted to, but that would be very expensive again. Like, binary gates are something that you probably wouldn't be doing pairing operations with. So what Ben Sasson and others managed to do is they found a set of pairing curves which can embed other pairing curves. And this, as far as I'm aware, this is the only set of curves at the moment which you can do this trick with. They're called MMT curves, and they're pretty powerful. Okay, one other property you might have of a snark is an idea called subversion soundness. So this idea that your protocol is zero knowledge, even if the setup has been somehow manipulated. Okay, you don't get soundness, but you do get zero knowledge. And this was a concept that was introduced in HDCrypt 2016, and it is very easy to achieve for snarks. The reason being that snarks are really small. So if you wanted to send lots of data about the thing you're trying to hide, you can't, because you're just not sending enough bits. So actually formally proving it takes a few more steps, a few more assumptions and all the rest of it, but it's usually fairly easy to adapt your scheme such that you satisfy this property. The thing that is not easy, and is one of the things that Sean was talking about in the previous talk, is soundness. So if you want to sort of say, even if there's malicious parties that are involved in the setup, we still should be fine. Nobody should be able to create bad proofs. And we're talking pairing-based snarks here, so typically speaking, they don't have trustless setups, but they can be updatable. I'm not going to go over that again because Sean already has. And likewise, they can be universal, so you can have just one setup suits all. You don't need to have a different setup for each application, and you don't need to rerun your setup if you happen to find a bug in your constraint system. I'm also going to skip this slide, I think. Oh, but I will mention this one. There was a subsequent work called Aurora Light that is also talking about universal and updatable setups. And this is based on R1CS constraints. So you do gain something because our constraint system, I think our polynomials are of size 6 or 7n, whereas this polynomials will be smaller. The downside with this particular scheme is you no longer have the fully succinct mode or even the partially succinct mode with the helper. You can only do it if you are having a scheme where you're trying to parallelize your proof generation. One other recent work in the literature, it's called Libra, is talking about sacrificing proof size for prover time. So this is something which you might sometimes want to do because the prover time is a big bottleneck in snarks. They also have a universal and updatable setup. And their techniques are based on a work called Proof for Muggles, which has been improved with some check protocols and lots of other papers since. So the way that they're laying out their circuit is very different from the way that we're laying out our circuit in sort of most SNARK-based things. And the advantage they get from this is because they only have fairly small polynomials at each step of their proofs of Muggles sort of protocol, they end up with very small FFTs, which they're actually running. And this is how they're able to claim that they get a constant-sized prover. And if you happen to have an absolutely huge system, which you run out of memory with, and you don't want to do distributed techniques, then it might be better for situations like that. So just in summary, there are a range of applications which SNARKs can be used for, and a range of properties that you can have. They can be small and fast to verify. They can definitely be parallelized. Most of what you're doing is multi-exponentiation, and this is just sort of begging to be parallelized. They can be made hard to manipulate between the sender and the recipient. This is something that you get for free pretty much in random oracle-based protocols, but is sort of a lot harder to achieve if you don't want to use a random oracle. They can be created recursively, they can be universal and updatable, and they can be made quicker to prove but slower to verify. Oh, any questions?
Hi, thanks. Is it possible and would it make sense to embed the verifier for the last SNARK you mentioned, which allows you to trade verifier time and space for proof of time in like a depth 2 SNARK like Groth 16? Would that make any sense?
So you would also have to embed the proof itself. And yeah, when I'm saying that the prover has reasonably low overhead, I mean compared to other SNARKs. I don't mean compared to computing the circuit itself. So it's possible that there might be sort of cool tricks you can do in order to make that work, but I'm not aware of them.
Thank you very much. Is the sapling SRS setup subversion safe? Subversion sound?
So the SNARK that they're using for sapling is Groth 16, right? Or is that Sprout? Is not subversion sound. They have to go through extra measures in order to have a one-time public key, which they then use to sign the transaction. But the actual setup itself, which they're doing in order to create the parameters, they have proofs of knowledge, and these proofs of knowledge are, yes, subversion sound, yes, I was thinking simulation extractability.